Gibbs free energy is named after Josiah Gibbs, who in 1875 proposed a thermodynamic quantity that combined enthalpy and entropy into a standard value. It was named Gibbs free energy. What is Gibbs free energy? Well, Gibbs free energy is defined as the energy associated with a chemical reaction that can be used to do useful work. Its units are kilojoules per mole. The most common formula for Gibbs free energy, which relates it to enthalpy and entropy, is delta G standard is equal to delta H standard minus temperature in Kelvin times delta S standard. For our first example, we'll find the standard Gibbs free energy of the dissociation of ammonium nitrate into its respective ions. Now we have the standard entropy and enthalpy of each of the compounds in this reaction. To find the standard enthalpy, we'll simply do products minus reactants to get a value of 28.05 kilojoules. To find the standard entropy, we'll do the same products minus reactants to get a standard entropy of 108.7 joules per Kelvin. Now we can plug our standard enthalpy and entropy into the formula delta G equals delta H minus T delta S. Now it's important to remember here to convert the entropy into kilojoules, and since we're at standard conditions, the temperature will be 298 kelvins. Now if we multiply all these together, we get a standard Gibbs free energy of negative 4.4 kilojoules per mole. The Gibbs free energy for any given reaction is the difference in free energy of the products minus reactants. It is more simply defined as delta G is equal to the sum of the delta G of the products minus the sum of the reactants. Now it's important to remember for these calculations that the delta G of any free element in its standard state is equal to 0. Now you should already know that in an endothermic reaction, one that absorbs heat, the delta H is greater than 0 and will have a positive sign. And in an exothermic reaction, one that releases heat, the delta H is less than 0 and will have a negative sign. Now this same naming can be applied to Gibbs free energy. An endergonic reaction is a reaction that uses free energy. Delta G will be greater than 0 and the sign will be positive. Now an exergonic reaction, one that releases free energy or has an excess, delta G will be less than 0 and the sign will be negative. This can also be used to determine spontaneity. Spontaneous reactions will almost always, with few exceptions, have an excess of free energy. Gibbs free energy can also be used to calculate the K constant of a reaction using this formula. The delta G at any given instant is equal to the standard Gibbs free energy plus the constant R times temperature in Kelvin has a natural log of Q or K depending on the situation. This relation of Gibbs free energy to the equilibrium constant is useful in determining spontaneity. If a reaction is spontaneous, G will be negative and the equilibrium constant will be greater than 1. However, if the reaction is non-spontaneous, G will be positive and the equilibrium constant will be less than 1. Now at equilibrium, the G is equal to 0 and the K constant is equal to 1 because the forward rate will equal the reverse rate. For this example, we'll be finding the equilibrium constant for this reaction of copper and silver. Now, it's important to note that this equation was derived from the earlier one because at equilibrium, the free energy at that given instant is 0. So you have your standard free energy is equal to negative RT, the natural log of K. Now, our G value is 8.871 kilojoules. It's important that it's in kilojoules. Our R is 8.314, and the temperature at standard conditions is 298 Kelvin. Now if we plug all these in, multiply them together, and solve for K, we get our K value of 2.81 times 10 to the negative 16. Now the standard Gibbs free energy can be used in the Nernst equation to calculate standard cell potential. Gibbs free energy is equal to negative N, where N is the number of moles of electrons transferred, F is Faraday's constant with a value of 96,500, and E is the standard E cell value. Now in this case, we'll use the standard cell potential of a galvanic cell to determine the standard Gibbs free energy value. Now if we balance the individual half reactions, we get an overall reaction of magnesium ions plus potassium ions plus water is going to yield magnesium oxide plus 4 hydrogen ions and solid potassium. The standard E cell value is 4.15 volts. Now part of the equation is the N. Where does the N come from? It comes from the moles of electrons transferred. In this case, there are 2 moles of electrons transferred. Now if we plug these values into our formula with an N of 2, a standard cell potential of 4.15, and for F, we use Faraday's constant, which is 96,500 coulombs. Multiply all these together, and we get a Gibbs free energy value of negative 800.60 kilojoules per mole. As mentioned before, Gibbs free energy is useful in determining the spontaneity of a reaction. As demonstrated by this chart, determining spontaneity is relatively complex, but it becomes simple when you use the formula delta G equals delta H minus T times delta S. So if you have a delta S value that's positive, delta H is negative, and delta G is negative, then your reaction is spontaneous at any temperatures. If all of the values are positive, then it's spontaneous at high temperatures. Delta G can also be negative in this case. Now all of the values are negative, then it's spontaneous at low temperatures, with delta G having the capability to be positive. Now, if your delta S is negative, delta H is positive, delta G is positive, then your reaction will not be spontaneous at any temperatures. Now, let's review. As you recall, Gibbs free energy is a value based on the enthalpy and entropy of reaction. It is the energy available to do work. It is the most commonly used in the formula delta G equals delta H minus T times delta S, but it can also be equal to negative N Fe and delta G standard minus RT times the natural log of K. Now let's apply what we learned and determine the E cell value of a galvanic cell made out of copper and zinc. Also, determine the standard enthalpy and entropy values of the reaction. The half reactions are given, as well as the standard G values. Try this problem now, and then I'll show you the solution. First, we'll solve for the standard E cell value. We have the half reactions, the delta G values, and the delta H values. We won't use those now, but they'll be used later. So first, you'll do products minus reactants to find the overall delta G for the overall reaction. Next, we'll use delta G equals negative N Fe. And we'll plug in our delta G value, an N of 2 for the 2 moles of electrons, and a constant F to get an E cell value of 1.10 volts. Next, we'll solve for the standard entropy of this reaction. Now we already have our delta G value, and we can find our delta H using products minus reactants. Then we'll plug in our delta G, our delta H, and our temperature of 298 Kelvin into delta G equals delta H minus temperature times delta S. And we'll find our standard entropy for this reaction, which is 2.098 times 10 to the negative 2 kilojoules per Kelvin.